Coutant LQT100 power supply unit. I've had this for at least 6 years. If I look at my YouTube channel, you can see me doing a very early introduction to the power supply unit. I picked it up pretty cheaply at a one of these sort of electronic fairs, and to be honest, I haven't done much with it. Firstly, it does work, but there is a small niggle that I'd like to try to repair, and hence I'm documenting it in this recording. About the unit itself, clearly it's a little worse for wear. It's probably 1970s or early 80s, two-channel power supply unit, provides 30 volts and 1 amp in each of the channels. So you can run it in isolation and have 2 separate channels. You can run it in parallel and get 30 volts at 2 amps or 60 volts at 1 amp, just by kind of connecting up the outputs in the appropriate manner. And it's very, very old school. It's just, lots of potentiometers, and you fiddle with the knobs and you get a nice little dial movement and so on. It's absolutely silent when it's running. In fact, if you look inside it, there's a big old transformer in there, nice linear, none of this switch mode stuff. Big capacitors, 2 identical channels, so the schematics and the circuits are spot on. And you can see it's really nicely made with the bound wiring, a little bit dirty, but heat sinks. There's the sort of the power output transistors. And yeah, the reason I have opened it, well, when I bought it, the guy did say that there was a problem with the constant current feature. I decided to pull this out and make use of it. It's a nice piece of electronics. And indeed, I verified that the slave channel works perfectly. And the voltage seems to be fine. It seems to be accurate compared to the meter reading. The constant current setting here, when you kind of flip the switch and you're monitoring how much current your unit's drawing, you can limit that. So if the unit draws more current than your limit, it stops it. And that works. On the master channel, again, the voltage seems to be pretty good. It seems to be maybe about a 1/4 volt under what it's represented here. So if it says 10 volts, you get about 9.75. If it says 20 volts, you get 19.75. Fine, okay, but the current limit circuit has no effect, and we'll show that in a moment. Now that means that in trying to debug this, and to be honest, I'm trying to go through the schematics and try to track what's going on. I do have the circuit description here. I have the original service manual, and this is the schematic, and we'll take a look at that. But basically, there are 2 identical channels. This is the master, and this is the slave. The only difference is that there's a couple of extra switches shown here, which is basically how the slave is tied into the master, if you're doing a series or parallel or tracking or non-tracking and so on. But I have the luxury of knowing that I have 1 channel which is working in every capacity. So if I needed to compare and contrast the 2 circuits and components therein, we do have a good version if we need to go there. But the reality is that having a chance to kind of open it and take a look, you can see some of the components down in there. And if you flip it over, obviously you can get to the bottom area. But I can't get to everything. And so really, to do a proper fix or test of the constant current control, I'm going to have to open it up. So that's what I'm bracing myself to do. Take the panel off. It looks like to get this unit out with the capacitor, the boards, the power output, all of that kind of leans out, I'm hoping. But to get to it, I've got to take these cross members out and they are screwed in behind the fascia. So I think the only way to really get into here is to take the front panel off, which means take the knobs off. This thing should pull off, expose those screws behind the front panel, and then unpick it, because these boards are then screwed in themselves, 4 places, 1, 2, and then 2 on the other side. Anyway, so while I try to unpick this to try and lean out the board and see what we can see, I'm trying to make heads or tails of the schematic. And yeah, we'll maybe spend a bit more time on this in a moment. But essentially, the schematic, you have your mains power coming in here, goes through a nice transformer, a little fuse, and the lamp filament, which itself, it works, but it's sort of intermittent. Maybe I'll replace that. There are 2 taps for each power unit. This one provides 22 volts, which is rectified, and provides what's called the ancillary positive rail, which basically is sort of the control voltage for the various circuits down here that control the performance of the power supply. The second tap here is the 32 volt rail, which I guess when rectified and smoothed goes then directly to the output source and then goes into your output terminals here and here. This is then the actual power supply delivery, 30 volts from here, controlled and throttled through these output transistors here. These are 2N3055s, which interestingly are the same output transistors or power transistors that appeared in the output stage of the guitar amplifier, the Torque Acoustic T100L that I repaired in another video. Okay, so you have your output going through here. Now you control the output. The voltage is controlled through here. Two potentiometers, a coarse and a fine. These 2 doohickeys here. And essentially, the output voltage is compared to the control voltage, if you like, in this differential amplifier, this VT5. And you can see that you have 2 common, these are basically 2 emitter, common emitter transistors kind of bolted together. They're actually in a single can. That means that these 2 things are matched together. They're thermally matched as well, because they're in the same can. And this differential amplifier looks at the inputs on the bases, which are basically identical. You can see that there's 470 ohms and 470 ohms, except that on this side, you have this chain that goes through the controls to give you some sort of influence over the current and voltage at this point on this side. That is compared with the output voltage, which is connected along here, up and then out to the output. And so by comparing these 2 values, when they're the same, the output here does nothing. But when there's a difference, it drives an amplified output here, which drives this VT4, which affects change on these 2 transistors, which controls the output stage. And that's working. So this sort of control circuit here for voltage, constant voltage mapping, seems to work, driving these 2 transistors on and off as needed to throttle the output. But when you come to the constant current, here is the constant current control, that knob there, which is one of these. And basically what that does is it looks at the sense resistor, this 1 ohm sense resistor in the output, and it looks at basically the voltage on either side. One side goes through the knob down into the base of this differential amplifier, and the other base, the other side of the base, if you go follow this chain up, it goes across, up, and basically comes into the other side of this R26 resistor. So by looking at the voltage on either side of the sense resistor, which is 1 ohm, you get an idea of what the current is going through that resistor, which is something that you want to influence. And so there's something in this chain which is not working, because when that differential amplifier senses a difference, there's a difference between the current coming out and the current that you want, then it affects a change on this transistor, this BC108 VT2, which then changes the drive on these two transistors to affect the output. But we know that those transistors are working because the voltage, the constant current, or the constant voltage workflow, which goes through these two transistors, is working. So I suspect that the issue with the constant current is somewhere in this transistor or the comparator, or something maybe with one of the transistors involved. I've checked those two. This R27, 10 ohms, that's working, that's okay. This pot works fine. It's a when you turn it up to 1,000 ohms, that's when you get maximum current coming through. And when it goes to 0, you have minimum current going through. And that's been validated by the working circuit over here. So that's a quick tour. But what is actually wrong, I don't know. I need to kind of get in, and those components in this as part of the circuit seem to be not visible. They're sort of in the middle of the board down there. So we're going to have to try and open it up and see what we can see. Just looking at some of the workmanship on this old power supply. Look at that. Look at those green resistors there. They're like a model of the perfect resistor. And then the way that they're put in, you've got that fantastic cut foot, like kind of like bent in. Look at that, there and there. I mean, think about putting that in. Usually you shove a resistor straight legs through, you solder it and cut it or something. And of course this is solder on the top side. So that's more of a kind of a mechanical holding. But that means you'd have to thread it through and bend it and then snip it on, and they do that everywhere, like those wires down there. There's another one down there. Lovely, lovely work. And the cable tying, literally I can say literally every inch of these wire bundles is cable tied, because it's about 1 inch spacing everywhere. Fantastic. All right, so let's take these grub screws out. Okay. Let's have a look here. Two. So the only way to get this fascia off is to take the knobs off and then pull it off over the switches and so forth. Why is that so stiff? Oh! Just debris. Just a bit of corrosion. I don't know. Looks a bit like miniature rocket. I like it. I'm going to put these controls knobs back on in the same switches when I'm finished. Give everything a bit of a clean up. So I'm putting them to one side on a shelf in the order that they came off, so I know which way they go back. And this one. Hope I'm getting this on film. Usually it's the back of my hand and people complain that they can't see. Oh yeah, it's another stiffy. Trying to understand why it might be biting so much, or fighting, I should say. Let's try it again. Oh, come on! Maybe a bit of WD-40 or something. Hey! Yeah, it's just metal on metal with a little bit of... Oh, I see. I can think if I... you can maybe see here. Hold the camera. Some grooved rings in there where it's been bitten into the probably can't see it. All right. So let's drop everything on the floor. Cool. I'll pick that up. Yeah. Pretty basic stuff. And yeah, I'll give that a clean and a dust. This neon lamp is a little intermittent. I don't know if it's, I mean, it does work. It's just, it seems to flicker and not, it takes time to warm up or something. I'm not exactly sure. But zeroing out, maybe we want to zero out the switches. We'll tweak. One of the thoughts I had is the observed voltage out of this channel, the master channel, is a little bit lower than the display. It's about 1/4 volt or 0.2 or 0.3 or something like that. So I guess what we can do is just measure this with an external source. I got a fluke meter, which I'll say is accurate, and then just tweak that display maybe from here or somewhere else. Maybe we'll see. We'll see if we can realign the output to this, unless that issue of the 1/4 volt is actually part of the problem inside the circuit to be fixed. But we'll take a look at that at the end. So what I have to do next is my thinking is, if I take these bolts out, I can loosen this cross member and see if I can get access to this. Another idea that I had actually was, you see the heat sink. The heat sink is, it's not in focus. It's kind of curious. There you go. Is bolted in 4 places to this frame. And if I can take those bolts out on tops and bottoms, I might be able to push the whole thing in so that the fins clear the bottom rail, lower it down so that the top clears this top rail, and then lean it out so it kind of hangs out a bit like that. Not exactly sure. We'll see what the next step is. I've opted to go for removing these crossbars. So I think I just need as much space as possible rather than working through a narrow gap. I'm going to try to pull it over here a bit. And if I do this properly, I can share with you what I'm looking at. Let's have a look. So there's a screw down here. Just see it. That's going to come out next. Yeah, coming, yeah. And then there's one on the back. Just lift it up a bit. Let me just sort out my supporting mat, cut mats on the bottom. This back one. Coming out pretty easy, actually. Only 3 screws because one of the screws is missing. So there's no screw at the top back. And I've taken out 1, 2, and 3. And in theory, should be able to walk this part out. Okay. Oh, fantastic. Plenty of room to have a look. Now, I'm conscious it's old wires, so let's be careful with bending things too far. But, yeah, lots of space. And, yeah, I'm going to leave it there and just double check that capacitors. These iPhones don't really focus very well, do they? I'll have to get a new camera. Check what's on that at the moment, and then we can get into there almost and do some checking on stuff, the values. Okay. God, focus, God. Okay, so I'm just trying to get this board separated from the heat sink so that I can take a look at these components. And there's a couple of screws down here. If I just loosen the screws, and you're probably looking at just the back of my hand as usual. You can see it just down here. It's just screwing into a standoff with a little, I don't know what that is. Is that a kind of a phenolic washer? Let's stick that in the pill box. There's one up here. Oh. Holy cow, man. I am the worst videographer in the world. But you get the idea, right? I'm going to do this one. I'm going to do this one. I'm going to do the one, or is it down there somewhere? And yeah, here we go. So I've separated the heat sink from the standoffs, and we can see the board, and it's upside down. Hang on. Stand by. Take it off the stand. I can see what I'm doing now. Okay. So, come around this way. There we have it. What you're looking at is VT3 and VT... let's have a look. VT3 and VT5 are the comparators. So these things here are the actual voltage comparators. And I want to know what they are, because I think maybe VT, pink one, VT3 could be bad, or VT2. Where's VT2? This little fella. Oh, where's the camera? This little fella here, or this one here, could be a little bit suspect. So I'm going to see if I can investigate those, and yeah, see if I can see any other parts that might cause concern. Certainly the cases are a bit rusty crusty. Maybe there's that sort of tin whisker thing going on inside them. I need to have a close-up look to see if I can find any identifying names or marks. There were some markings on the cans. I can't read it from here. 41512 SO2 or something. I don't know. Let me have a look if I can get a good picture of those. The problem is on this board somewhere. Well, it's been about 2 weeks since I started recording this repair job, and I guess this video could be in two parts. The first part, which you've just seen, is me faffing around trying to figure out how it works. I'm trying to pull apart it. I test things in circuit. Yeah, I'm floundering. I don't know what I'm doing, right? This is me. This is the guy who's got an interest in electronics, trying to repair stuff and have a go, and I'm learning. And so, I'm sharing this video, warts and all. Basically, if I take a step back, I have done a bit more research and a bit more learning about what's going on. The original user manual or circuit and circuit description for the LQT100, the two-channel model, didn't really share much insight to me about what was going on in these circuits. But it turns out, of course, that Coutant made lots of power supplies, and they made a single-channel version, which I picked up a couple of weeks ago. And this is the LQ100. This is a beautiful example. It's working very nicely. But it had its own circuit diagram, and circuit description as well, which was much more helpful in informing me about what's going on in the circuit, because they share the same circuit. This is just a one-channel version, and it has basically exactly this circuit layout. So reading the manual for the LQ100 gave me better insight into what's going on here. And essentially, for the constant current comparison, you should keep an eye out on this rail here. This rail is the reference rail and should equal your output voltage. So it comes up to here and then out to here, okay? So there's your output voltage, should be on this rail. And then you've got 3 Zener diodes, 1, 2, and 3, which provides 15 volts surrounding your output voltage. And those 15 volts drive the comparison circuitry. So as your voltage goes from, say, 10 volts to 20 volts to 30 volts, that 15 volt framework will rise or fall following your output voltage. You're going to see a clip of video where I'm testing that line in the slave, which is working well. And in fact, I test this point here on the cathode of MR12, the diode, which should be connected to the output, and indeed I get exactly the same voltage. So this voltage line should be the output. But in the affected channel, this output voltage is about 1.1 volts higher. So if I suppose 10 volts on the output, if I measure the output, I'd say roughly 10 volts. Then if I measure the cathode of MR12, which is there, I get something higher, about 1 volt, 11.1, so 1.1 volts higher. And that's curious, because I don't understand why this, if it's electrically connected, would be different. It's not different in the good channel, but it is in the bad. Now, when this is higher, 11.1 volts, it creates the reference voltage for your comparator at 11.1 volts. and it creates a 0.7 voltage drop here. You get about 10.4 volts here, assuming a 10 volt output. But on the side that you control, there's your constant current limiter control. You create a voltage divider between your output voltage and this base. Ultimately, this voltage here can never compete with the 11.1 volts here. Obviously, this is being taken from your supply, you know, about 10 or 10.2 volts compared to 11.1 volts. Basically, it means that this comparator is always off. This side of this transistor is always off, and this side is always on, and therefore you get full current. So the control issue isn't the problem. It's the reference voltage which is a problem in this particular channel. So now the hunt is on to try to identify, why is this rail 11.1 volts if it should be electrically connected to the output? It certainly exhibits that property in the slave, which is working well, and the constant current comparator is working well. So let's see if I can figure this out. The next clip of video you're going to see is just me testing this side and showing indeed that the output is correct. So, as I said, this might be a long video. No one's going to watch it, but it's instructive to me. Okay, so just to check something, on my second channel, the slave unit, which is working fine, I've set up 10 volts into my dummy load, and I'm just measuring, if I can do that here, I'm measuring the cathode of one of the diodes, and you can see that it's 10.2 volts, okay? Now the cathode that I'm measuring is this one here, right there. Well, actually, it's the second channel, and it's this cathode here, which should be connected, if I follow this out, should be connected to my output voltage, and it should represent the voltage on this reference rail. Now that, as I said, that voltage that I'm measuring is 10.2, and indeed, if I just swap the cable over and I go for this one, then if I put that in here and we measure the output voltage here, 10.05, 10.0 whatever, 4. So the output voltage that I've set for 10 volts is actually being represented there on the cathode as well. So this output voltage is being measured here. It's the same. And that's not happening in this master channel. This voltage here that I measure at the cathode is 11.1 volts. It's higher. And that's what's causing the problem. That means then that the voltage being used as an input voltage here, so it comes off this 11.15 volts, comes down to here as an input. That's the reference voltage, which is much too high. The actual sampling voltage is correct. I mean, you can twiddle your current limiting resistor here and get reasonable volts, which you can then compare, but you're comparing them with a much higher voltage, and therefore this transistor is always switched on, this one is always switched off. So I think the comparators are working fine. If the question is, why is this voltage so much higher? It's 1.1 volts. It's as if there's something between the output voltage and this point here, which is not evident in the diagram. Maybe it's a capacitor somewhere, because there's quite a few capacitors on the output which are not listed in the diagram, circuit diagram. There's no real capacitors across the outputs here. Something is drawing a current, and therefore, if this is 10 volts, it's increasing the voltage to here, and that's the problem. So I need to find out what is creating a voltage increase of about 1.1 volts. And that might actually fix it, because it's definitely not happening over here. Okay, so indeed, hunting high and low. focusing on why this voltage is not electrically connected to this voltage over here, output voltage. So I started doing some forensic light tracking of this trace and seeing where these components connect. Of course, in the back of my mind, I'm thinking maybe the schematic isn't fully accurate and doesn't represent what's on the board. Maybe there's some other components added here. But in truth, I think I found the problem. I think that there's a disconnect between, well, this point here and the output. And indeed, if I can get down here, I don't know if I can show it to you in this picture. There is a gap in the trace just there. Just, you can see this, I don't know, just below the tip of a pen. There is a gap in the trace right there. And I don't think you can see it in this shot. Oh, maybe it's right in there. So let me try and zoom in. There it is. There is the broken trace. And so I need to repair that. That break essentially is breaking here. This from the red dot there or down here. There's basically is a break right there. Okay, so I'm going to mock up a little jumper cable, and then we'll switch it on and test it and see if that fixes the voltage issue on this line, which then affects the reference voltage, and maybe this comparator will start to work, and maybe we'll see if the current limit is fixed. Fingers crossed. Okay, so let's test the fix here. I've just got a small jumper cable replacing the broken track for now. We are on the master channel, which is here, getting 10 volts, near as much. There you go, 10 volts. Spot on, to be honest. I quite like that. Then into the 50 ohm resistor, I'm drawing 0.2 amps, which is pretty good. 0.2 amps. And let's try the current limiter. This is here. So if I turn it, start turning it down, left, 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 keep going until, oh, there you go. No limit. It stopped. And the voltage has died. And if I open it back up again, big enough to draw 0.2 amps, we're back to the 10 volts again. And if I just start to throttle that current, there we go. So what, at about 1.1 amp, it's throttling it to roughly 5 volts, 4.5 volts, which is what you'd expect. So yeah, that is a fix. Broken trace, that's all it was. Well, I learned how to troubleshoot a bit more today and read schematics and have belief that I can do these sorts of things. So thanks for joining me on this, and let's troubleshoot something else together. Thanks for watching. Just showing the repair trace. You can just see it there, that little bit of wire. I think that's a fairly neat job. It's enameled wire, tinned at both ends. I had to make some space by taking these wires off, and I'll label them and I'll put them back on, and it shall live again. Cool. And finally, yeah, putting it back together. You can just see the green enameled wire back in there, and it is good to go. So pulling 15 volts, looks right, into a 50 ohm load, should be 0.3 amps. The meter's pulling a little bit high. I could probably adjust that. There's an adjuster I think, to control the current flow. But we're interested in the current limitation. So let's go 20 volts, drawing, okay, nominally 0.4 amps. And then if I turn the knob, oh, there we go, cutting the current. And if I draw 0.2 amps, I should reduce the current to about 10 volts, okay? 9 point something. So if I tweak this a little bit, because the meter seems to be running a bit high, yeah, 10 volts. So constant current limiter fixed. Love it. Lessons learned on this build: don't trust in circuit measurements of semiconductors. Don't be quick to think that because it's an old supply that all the components are old and everything must be pulled out. I haven't changed any capacitors. I haven't changed anything. All I did was fix the broken trace. So I've learned something on the build. I hope you found it interesting. And if you have one of these, hold on to it, because they really are well made. As far as I can tell, having played with them now for a little bit, easy to service, as accurate as you need for, home use. This is probably, plus or minus 5% at best, but maybe we can tweak it a little bit and get a bit closer. Yeah, I liked it so much that I bought the single channel as well. There we go. So that will be my power supply going forward. Oh, one thing I won't show, I got to fix this bulb. This bulb is not working. Not so easy to get into. You can see, bring the light over. The bulb sits right down there. You see the glass bulb with two red heat shrink legs over the wires, and those wires seem to be extended into green. And then, yeah, you got some wire just clipped on. I can zoom in a little bit. Clipped on to there you go. A little tricky to get into that, actually. I'm not quite sure how I'd best do it. Bit tight. So while I peruse the options to replace this, I'll bid ye farewell. Thanks for watching.